I will now look at a transient thermal analysis of a thick steel cylinder using ANSYS Workbench. This cylinder internally has, let's imagine, boiling hot water at 100 degrees with a very high heat transfer rate, and at the outside it's exposed to, let's say, air at 20 degrees with a heat transfer rate of 50 watts per meter square Kelvin. So it's a steel material, and Young's modulus, Poisson ratio, etc. are familiar, but we should also be familiar with the thermal expansion coefficient, heat conduction rate, the specific heat, and the density. We need all these in terms of doing a transient thermal analysis, and then later we can look at some stress analysis for this example. We'll create an axisymmetric model. Initially we'll make the whole cylinder at 20 degrees, and we are going to apply that 100 degree internal boundary condition, let's say suddenly, through that heat transfer rate, and we'll solve for a single load step for about 1200 seconds with certain time increments. So we'll look at how to set up this problem and solve a transient thermal analysis. In Workbench, we'll drop our transient thermal analysis system onto the project schematic, and for the geometry we're going to create a 2D axisymmetric model, so we need to make sure that the analysis type is changed to 2D, and then we can start Design Modeler. The geometry is again quite straightforward. A simple rectangle will do. We can look at the drawing plane from the front. For an axisymmetric model, we need to ensure that the model is done on the XY plane and on the positive X-axis side. So we can go to sketching and create a rectangle. Let's first of all zoom in somewhere here, and we can create our rectangle. I'll do it arbitrarily, but constraining it to the x-axis, and then I can add my dimensions. So the thickness of this was 50, so I can define h1 as 50 millimeters, which is 0.05, and the internal radius is 200 millimeters, so I can define this value h2 as 0.2 meters, and therefore the outside radius is going to be 0.25 meters. Now the height of this isn't that critical. We can, just for illustration, make it 200, let's say. If we go and define a vertical dimension from here to this line, so V3, let's make that 200. Of course, in terms of meters, 0.2. So that is the rectangular sketch representing an axisymmetric model. So if you go to modeling on the XY plane, this is the sketch, and we again need to do a surface that will define our axisymmetric model, and we don't need to define thickness, it's not relevant for an axisymmetric model, so we just need to generate. So this is the sketch that will move to Design Modeler. Now I have started Mechanical from the Workbench project schematic, and the design modeler geometry is transferred, so we got just one surface body, and material by default is our structural steel, and we can define our mesh on this one. So if we go to mesh, which is our context, we can define a sizing. We can say on this surface, make the mesh element size 0.005, so that's about 5 millimeters. So if we did generate on that mesh, it creates around 10 elements through the thickness. Now we can see this is a two-dimensional body, but it's showing as a 3D representation. Initially it's assuming it's a plane stress model, or a plane model. If you go to geometry, we need to change that from plane stress to axisymmetric. Now when it's axisymmetric, it's still showing as a linear body, but what we can do is do a symmetry expansion on this one. So for this one, you'll need to have something turned on the workbench options. So I'll first go to workbench. If you go to tools, options, and appearance, if you scroll down on this one, if you turn on this beta options, make sure this is checked, it allows us to define a symmetry expansion. So what we can do in our model is to insert symmetry from this list. So once we insert symmetry, we can define what type of symmetry you want to see. Now obviously this one isn't Cartesian, it's an axisymmetric model, so we can do 2D axisymmetric, and delta theta is the say 10 degrees, so it will create 10 degree increments up to 37 times. So if we did that, that'll actually show us a 360 degree model. We can instead show just 19, and that will be a more representative, let's say, or easy to see, visualize half pipe, so we can see what's happening on the inside surface. So that's our symmetry expansion. The model is 2D. It's a two-dimensional model, and it's only defined on the XY plane, on the surface. But we are effectively creating an axisymmetric expansion of this 2D model. Okay, so this is our geometry and the mesh, and what we are going to do next is to define our boundary conditions. Now this is a transient thermal analysis, and initial temperature is important. We need to make sure that this is defined, let's say 20 degrees for our model, and the analysis settings simply say how many steps are there in this model. So I'm going to create just a single load step, but with a few sub steps. Step end time, I'll need to define this in terms of real time, so that's 1200 seconds. And automatic time stepping, I'll turn that on, and I'll define it in terms of time. So initial time step, that's a pretty small value, it's like 10 milliseconds. I need to change that to 10 seconds. Minimum time step, I'll make that the same, and the maximum time step, I'll make that the same as well. So it'll create a solution at every 10 seconds, and time integration by default is going to be on. So this is my analysis settings, And what I need to do next is define my boundary conditions. So they'll be dependent on time as well. So the first boundary condition was convection and the inside surface. So I'll need to select the inside face. So let's say change our view, select our inside line and apply, and the film coefficient was in terms of 3000, and check the units, that's watts per meter square centigrade, that's fine, and the ambient temperature was 100 degrees. So that is the inside the cylinder 100-degree fluid with a high transfer rate from the fluid to the steel body. Now that value, both the convection coefficient and the temperature, is constant from time 0 to time 1200. So you can see how that is changing over time. So the next boundary condition is another convection, but this time it's at the outside face. And what we wanted to apply was 50 for the heat transfer rate, and the ambient temperature was 20 degrees. So make sure that geometry is applied. And if you don't apply anything at the top and bottom lines, that assumes that it's an adiabatic boundary. That means there is no heat being transferred from this body in this direction. So this is essentially an insulated boundary. So this is what we need in terms of our boundary conditions. And in the solution, we want to see our temperatures and our heat flux, and we can also see how the heat transfer changes. So if we drop this convection to the solution, that creates another reaction probe, and with the convection 2 we can also drop that, and it creates a reaction probe on the outside face. So that's essentially all we need to do to set up this transient thermal analysis, and we can start the solution by clicking solve. So let's look at the temperature, and we can see that the green, blue and red are defined here. The blue one is the average, I don't need to see that one, but what's interesting is the minimum and the maximum values. So minimum is the red line here, and that's changing from around 20 degrees going up to around 90 degrees, and the green line is changing from around 50 degrees to about 1200 at about 1200 seconds, going up to about 98 degrees. So we can animate this, and that means how the temperatures have changed in time. So the most changes happen in the first few seconds. So there's a sharp thermal change, and we can actually make that, let's say, 100 frames and animate it over 10 seconds, and then run this. So that gives a more precise change in temperature. Now after about let's say 400 seconds or so, it looks like this has reached transient this transient analysis has reached a steady state. Let's say 500 seconds, we can do retrieve this result set, and at that time the inside face is about 97 degrees and the outside face is about 93 degrees. And we can look at the tabular data that corresponds to time 500, and also it shows us the minimum and maximum values. We can scroll at the bottom of the table and see that at 1200 seconds the inside and outside or the at 1200 seconds, the outside and inside temperatures are just about 4 degrees apart. So looking at the heat flux, initially there will be a large heat flux. That's due to the fluid heat being transferred to the body and heating it up, essentially storing that energy. And if you look at the reaction probe, and that shows us how many watts of energy is being transferred from this fluid to the body, and it reaches a steady state. So there's about 1100 1200 watts almost of heat being transferred from this body to the outside surface. Remember, that was for only 200 millimeter long cylinder. So if you had 400 millimeter long cylinder, that amount of heat will double. If you look at the reaction probe on the outside, you'll see that that is becoming a negative value. So the outside face shows that heat is being given off from this surface to the exterior, essentially the air. So this concludes the transient thermal analysis of a thick cylinder.